All right, starting on chapter 4 now. Now, we left off on the last chapter talking about two really important scientific laws, the law of conservation of mass and the law of definite proportions. The reason these are so important is that they are extremely strong indicators that there are these little things called atoms, that there is a smallest building block of matter that we're dealing with. And so, late 1700s, there was lots of experiments going on with gases, and it was really, really supporting this idea of atoms. And then, early 1800s, a guy named John Dalton came around and established what we now call Dalton's atomic theory. So, let me tell you about that. There's a bunch of little postulates to it. So, the first postulate of Dalton's atomic theory is that each element is made up of these little tiny indestructible particles called atoms. Now, some books, if you look at it, will say indivisible, sometimes it's indestructible. Kind of the same thing, though. But these little unbreakable bits that are called atoms. Atoms of a given element are all going to be exactly the same, right? So if I have like 10 oxygen atoms, they're all going to be exactly the same. But atoms of different elements are going to be different in at least one way, possibly more ways. So that's postulate 2. Cruising along here. So you got chemical compounds are formed when atoms of different elements combine with each other. Right, a given compound always has the same relative numbers and types of atoms. So I like using water as an example. So there's always 2 hydrogens and 1 oxygen. Right, that's what makes water water. If it's 2 hydrogens and 1 sulfur, it's not water. If it's 3 hydrogens and 1 oxygen, it's not water. All right, so a given compound will always have the same relative numbers and types of atoms. When you have a chemical reaction, that's just the reorganization of the atoms. Like, it's how they're connected, how they're linked up, how they're arranged, their geometry, all that stuff. They're just moving around, but the atoms themselves are not changed, so they're not created or destroyed. So when I think of this, it's kind of like shuffling a deck of cards. So you take a deck of cards, you split it, right? So the pile of cards in your left hand, that's like one of the reactants. The pile of cards in your right hand, that's one of the reactants. And then when you shuffle them all up, you stuff them back together, and then you split them again. They're different, but like none of the cards have disappeared. There haven't been any cards that have appeared out of nowhere, but they've been changed. The piles are different now. There's a different ordering to things, and that's what goes on with chemistry. So all the atoms that are there when you start, they're there when it's all done, but they've just kind of switched how they're connected, and by doing that, it changes all the chemical and physical properties. It's kind of cool. All right, a little mini concept check here at the end. All right, so Dalton's atomic theory, it's a couple hundred years old now. Do we still think all that's true? So do we still believe that elements are made of tiny particles called atoms? Do we believe that all atoms of a given element are identical? A given compound always has the same relative? Like, which ones of these are true? Which ones are not true? Let's go with that. Think, keep pondering. All right. How about all atoms of a given element are identical? Here in Albuquerque, we have a baseball team, isotopes. All right, we now know of something called isotopes. So they are atoms of a given element, but they're not identical. There's something different about them, and I'll get to that later on in this chapter. And down at the bottom there, atoms are indestructible. They're not indestructible. We can crack them apart. So that's that for the first little chunk here. All right, I'll catch you on the next one.